Now we have the classical curves. Crazy because I came in today and I saw a classical curve right here. It's a transformed classical curve, but it's pretty much the right idea. Let me send that out real quick. This might fall under the category of like, you look back on this picture, like a few weeks from now, you're like, he sent a picture of a rubber band. Why did he send a picture of a rubber band? But yeah, that's what I did. Right? Because what this picture is really getting across the idea of a limason or limason, is actually how it's pronounced. But like I can't not see lima bean, so I see that and it's lima. Now I do remember one of the like the 4 things I remember from French class, all 5 years of French. That little almost number 5 underneath the C, that softens the C. It's Sevilla, I think. But whatever. But that little symbol, it takes a hard C and makes it a soft C. So it's definitely son. But the lima or lima, I leave that up to you. The other ones I think are pretty obvious. Rose, cardioid, those sound about right. This one, the way you would make up the phrasing, the pronunciation of it is exactly how it's pronounced. Lemniscate. Like that's just what it is. Right? And then the spiral of Archimedes. Right? I suppose the last one you wouldn't know how to pronounce if you'd never heard of Archimedes. Right? Or ever seen that word written, or I'm sorry, spoken out loud. I had that experience because I read a lot of books when I was younger, but I never heard the word spoken out loud. So like A-W-R-Y or rye. Yeah, I thought it was Ari because I'd never heard anybody say it before. And we didn't have like Google pronunciations, like you type the word in and you just click on it and it says it for you.
Those don't even always work.
Yeah,
sometimes they can be like the verge version and it's real, and it's like, this is not.
It's complete hit or miss sometimes, but yeah, there's some words I look at, I'm like, oh wow, that's how you say it. And it's like 30 years later, so, you know, it's entirely possible. But the moral of the story here is, I mean, it really doesn't matter what these things are called. It's more so that there's an equation that corresponds with a picture. Now you may look at it and say, okay, well, couldn't I just put the equation in my calculator and then learn the characteristics that way? And then my answer to that would be like, yeah, that's a great idea, let's do that. Right? So let's take a look at number 11, r equals 3 plus 3 cosine theta, and see how one might go through the process of graphing it in their calculator. All right? Understanding that it is definitely a little on the, I don't want to say tricky, but it's a little different than the way you would create a graph in function form, right, rectangular form. Because when you would go to the table to grab some points, even if it was a decimal, you still know it would be left or right and then up or down. All right, there wasn't as much guesswork involved. Here, there's a little bit more guesswork. So let's investigate. All right, so I don't know why. Maybe that's why I put it away. All right, so I'm putting mine in polar mode. All right. Radian. Yeah. Now you really have license to go either way, because when I told you that I was going to give you this graph as is to create your sketches, that tells you that you're going to get the radians and the corresponding degrees. So you want to work in degrees, work in degrees. You want to work in radians, work in radians. The only time you need to be in radians is when you're dealing with a non-trigonometric function along with a trig function, right? So let's say you're in function, a rectangular form, and you want to graph y equals x squared, keeping it simple, along with some trig function. all right? Because the units don't jive if you have your calculator in degree mode, because then the scale goes up to 360 degrees, and then your line's going to be all out of whack, all right? Or in that case, your curve. So yeah, you want to be in polar form. Radian, if you don't feel like changing it, yeah. And so that's what I'm going to do. Y equals, again, becomes R equals. So 3 plus 3 times the sine of theta, times the cosine of theta, sorry. Now there are characteristics related to these classical curves that allow you to come up with a sketch without really doing what we're about to do. But this technique is always going to work, so there's that. But also, you want to have a way to investigate these characteristics on your own, not just have, you know, a chart to rely upon. All right. So I'm going to hit graph, take a look at the picture. Now again, so this is where my app differs from your calculator. I don't have a zoom function. I just have a thumb and an index finger. So I can get it sized up the way I want by doing it that way. All right, so let's say you don't have a touch screen to work with. Zoom 6, standard zoom. All right, let's see how it goes. Zoom box, yeah, zoom box will work. Yeah, so just as long as it's going to be around 0, you know, in that somewhere in that -10 to 10 neighborhood, you're going to be fine, because none of these graphs are extreme in terms of their scale. All right. So yeah, so there's that, and you can also manually manipulate the window, but I would say you hold off on that idea until after we talk about what about the equation tells us certain attributes of the graph. All right. So what we're going to do is create a table of values, because I got to get this on paper. So the table of values is it's as easy as you want it to be, basically. It's kind of tricky though, because it does call upon prior knowledge, and that prior knowledge has everything to do with the unit circle. All right. Now, one thing that's kind of a little bit of a weird component is when you plot coordinates, x comma y, x is treated as the independent variable and y is treated as the dependent variable. All right. But here you plot r comma theta, but theta is the independent variable. All right. So it works the other way around. So what I want to do is I want to grab some theta values. I want to grab me some theta. And I'll start it off at 0. And I'm going to start working my way around the circle. And here's the important ingredient. I'm going to use only convenient values of theta for cosine. And you're like, okay, the hell does that mean? So thinking in terms of the unit circle, at least to start, I only want values of theta that are going to give me cosine ratios that are nice. Nice. So basically, I don't want radicals, because radicals means decimals. Decimals mean estimations. Now, I might resort to that, and that's perfectly fine, but I don't want to go to that as a default, all right? So the first relatively clean one is pi over 3. And that's because cosine of pi over 3 is equal to 1/2. All right. Another one is pi over 2. So it's going to boil down to the quadrantals, so anything on an axis, and anything that has a denominator of 3. All right. If this were sine, I would go with denominators of 6, because pi over 6 is clean for sine. But if I did pi over 3 for sine, I'd have a radical 3 over 2. I don't want that. Now, there's nothing wrong with it. If you grab that value and you got a decimal and you had to estimate, you did not do it wrong, I promise you. It's just, it's not a nice set of numbers. Right? So it's really what we're after here. All right. So next up would be 2 pi over 3. Then pi. And then so on. So I'll leave it at that for the moment, because where I'm at this point, I just want to see. Yeah, I think I'm going to have to switch over to the ordinary graphing calculator, because what I'm about to show you is not going to work on this. What can you do? What can you do? So, in your window, so second window, table set, we're going to change. So this is not the ideal approach, but this is the way we're going to do it. We're going to change our delta table. We're going to make that pi over 12 so that it counts based off of what we have in the on our graph grid. So you're going to change you're going to make your delta table pi divided by 12. And then go back to the table the start should have been 0. I don't know why my start isn't 0. There we go. Now it's 0 for some reason. I have no idea. All right. So again, not ideal. I'll talk you through the other approach in a couple minutes, but for now, I'll just get you going on this one. Every line segment up from the polar axis is equivalent to pi over 12 units. So pi over 12, 2 pi over 12, 3 pi over 12, 4, 5, 6 pi over 12, and so on. So all you're doing is counting down steps corresponding with the position here. All right. So I'm taking it a step further and only grabbing the convenient ones. All right. So 0 pi over 12 I know is 6. Then 1, 2, 3, 4 pi over 12 is the next one that I want, the pi over 3. So 1, 2, 3, 4 pi over 12, that's 4.5. All right, so it's taking all of my need to do any calculation out of the equation here. So 0, 4.5, 2 more movements, and I'll be at pi over 2. So that's 1, 2, and that gives me the 3. All right, so all we're doing is counting. What we're not doing, and this is the important thing, what we're not doing is any thinking. All right, all the work is mechanical, it's rote. All right, so 2 more steps, go down 2 more steps, see what comes up. 1.5. I'm at 2 pi over 3. 1, 2, 3, 4 more steps will get me to pi. And that's going to be 0. Now, you could look at it the other way, because, and that's kind of the moral to the story here. We came up with these values based off our knowledge of the unit circle. Find the clean ones for cosine. But by establishing the step, the change in table as pi over 12, we made it so that the theta is going to increase corresponding with movement around the polar graph, which is great. The nice byproduct of that is it allowed me to just go through my R column and say, I only want the clean ones. Now I can go back the other way and say, all right, I had no idea what the angles are supposed to be, but I do know that X number of units corresponds to 0. And so now I can plot the points that way.
I got 6 for 0.
You got 6 for 0? Oh, I think I did 2. I think I just wrote 0 for some reason. Let me just go back up. Yeah. Because in retrospect, that felt right. All right. So what that also tells me is that the table of values is more of a luxury than anything else to kind of get a feel for things. I can just work off the table in my calculator. Now, what I was going to show you on the graphic calculator has to do with actually deciding on these values first. Once you decide on them, you can, in your second window menu, change it from auto to ask. And then it allows you to just type in what values you want and create a table, a unique table of values out. It's just this doesn't seem to have that setting. So, and for whatever reason, I can't show it to you on this because every time I put that in, it hijacks the whole feed, and I can't display the computer monitor anymore. And this is literally the only room that happens in. So I don't know what's wrong. Anyway, we'll do it this way for now. In next class, before I hook up the iPad, I'll try to show you the other technique. So I could go down my list and say, okay, I have 6, 0. That's 6 steps in the direction of the theta value of 0. So here's the theta value of 0. I'm going to go 6 steps in that direction. So 1, 2, 3, 4, 5, 6. So it's going to be about right here if I'm ballparking it. All right. The next one that's important, I mean, I guess they're all important, but the next one that I care about, because remember, these coordinates are written as 6, 0, 4.5, pi over 3, 3, pi over 2, 3 halves or 1.5 if you want, 2 pi over 3. It's always r then theta, 0 and pi. So the second one is telling me that I'm taking 4.5 steps towards pi over 3. So towards pi over 3, 1, 2, 3, 4.5. 3 steps towards pi over 2. 1.5 steps towards 2 pi over 3. 0 steps towards pi, well, 0 steps towards anything is going to leave you at the pole. Now, I only came up with these points, but my graph looks like that. So what we're going to do is rely on symmetry and a little bit of common sense. Well, maybe the common sense first, then the symmetry. Because it's got to look like this. It seems as though we have the top half of that. All right, well, in order to look like that, it would have to be basically a reflection in the bottom half. So I'm going to reflect all of these points over the polar axis, and that's going to give me the bottom half. Now, if I didn't want to do that, that's fine. I could just keep going down my table, just keep in the down arrow, and grab more and more points, and eventually I'll have everything I need. But if you can kind of make that realization, you can save yourself a little bit of time. All right? So the important angles, that's how you're going to get your reflection. So let me highlight. We're looking at pi over 3, which means we're also looking at 5 pi over 3. We're looking at 2 pi over 3, which means we're also looking at 4 pi over 3. All right, we had pi over 2, which means we also need 3 pi over 2. All right, so reflect the angles and then use the same steps in those directions. All right, so we did 1.5 steps towards 2 pi over 3, so let's do 1.5 steps towards 4 pi over 3. We did 3 steps towards pi over 2, so 3 steps towards 3 pi over 2.
4.5 steps towards pi over 3. So 1, 2, 3, 4.5 steps towards 5 pi over 3. And then a nice smooth curve through all of it. And then you have your boom shakalaka moment. That's the best I can draw, so. The good thing is I won't hold you to any standards that I can't hold myself to. So if your graph looks even in the neighborhood of that, it's a full credit graph. All right. So you have this picture, it corresponds to this equation. You compare it to the table above, and you start asking, okay, well, what do they just graph, and why is it important? All right. So we're looking at different possibilities. I might as well bring it in a little bit because it's hard to see. Well, we have one that talks about a plus a cosine theta, a plus a sine theta. And that's your cardioid, right? Now you can see that the limacon has similar characteristics, except it requires the coefficients to be different from one another, right? So it is possible that you could have a limacon that looks very much like a cardioid, but in order to be defined as a cardioid, the coefficients have to be the same. So if you think of the cardioid as a special type of limacon, where first off, there's no inner loop-de-loop, so visually that's your difference, but also you're talking about something, where the coefficients would be exactly the same as opposed to being different. So same structure, but same structure, but also same coefficients, making it a cardioid. Am I going to ask you to name these things? No. So it really doesn't matter in that regard. But if I start using these terms in class, I don't want you to be caught off guard. Also, we start getting into things like horizontal and vertical tangents and the calculus of it. If I start getting into derivatives, I see I have a vertical tangent here and here. I have a vertical tangent there, so 3 of them, and a horizontal tangent here and here, and I even got a cusp. So there's a lot of calculus going on in this one diagram, right? So we're going to have to investigate that stuff also, all right?
I see on the board that for the limacon still is an addition for the sine theta, but on the printed copy we have a negative, or you could a negative b sine theta. Is that a plus?
It should be a plus. Yeah, it must not have come through in the dot.
Oh.
Yeah.
So the all addition.
Yeah. The old picture of a picture business. I got this from some website somewhere. Probably could have typed it up and made it look nicer, but I didn't. All right, so the remaining problems here are all basically doing the same thing, coming up with values to graph and all that good stuff. So I'm going to put a nice star. It's something that was kind of, I don't know how to describe it. I mean, in my classes, I always hit that concept hard, emphasize the importance of it. You need to know this. You're going to thank me later, all that stuff. I lay it on pretty thick. And then a couple of courses go by where you didn't really have to know it. And then all of a sudden you come to a course where you really do have to know it. You're in that course now, all right? This is that course. The one course, the culminating course of all that unit circle stuff, where all those promises that teacher made, whoever it was, will come to be fulfilled, right? So if you actually did what you needed to do, right? Now, if you've been dragging your feet on that, you're like, yeah, it's on my list of things to do. I'll do it next time. I'll do it next time. I'll do it next time. Well, there's going to be a reckoning, right? We don't want that to be on a unit test, right? So I'm gonna sort of manipulate you into learning the unit circle if you haven't already done so. But like I said, I'll talk about that in a little bit, all right? Because I've been
promising to talk to you about a bonus opportunity that's unit circle related, and also there will be some quizzes that are on the unit circle. So I'll give you the full breakdown of what those are all about in a little while, and then I'll talk to you about when those are going to occur. All right. But for now, you can kind of rest easy in that the moment of truth hasn't occurred yet. We could still rely on the calculator. But when you're coming up with the graph, again, you want to have a sense. You want to be thinking, what are my points? What are the good points that I want to use when I'm generating this graph? Right? And so if you have a good feeling about the unit circle, then those points come easily. If you don't, they don't. All right? So theta values that are convenient to sine. All right? So anything on the axes is going to be convenient for any function. All right? Sine, cosine, tangent, and all the reciprocals. All right? Anything with a 30-degree reference angle is going to be convenient for sine. All right, so we're talking, so I'll start with 0, pi over 6, and again, you might want to go degrees. It's up to you. So you might say 30 degrees. But then I would jump to pi over 2, then 5 pi over 6, then pi, and then I'll take a look at the landscape and see what's going on. All right, I don't want to go too crazy, because if the trend that develops based off of the nature of these points steers me towards the entire graph, then I'll be in pretty good shape. All right, so I'm actually going to do this out by hand, just to do it out by hand, because the last one I didn't. We went to the calculator, so I want to be able to say, you know, it'll let me sleep at night that I went over some unit circle trig type problems with you. All right, so 4 minus 4 times the sine of 0 is going to be 4, exactly. So 4 comma 0 would be our coordinate, because r comma theta. Now I don't want to jump to plotting that yet until I get a sense of scale. All right, maybe this is the furthest point out, but maybe it's not. All right, so 4 minus 4 times the sine of pi over 6. So sine of pi over 6 is what? 1/2. So 4 times a half is going to be 2, so 4 minus 2 is 2. So 2 comma pi over 6. All right. So scale-wise, we're still pretty good with the ordinary scale. We won't have to go by 2s or anything like that just yet. If at all, we'll see in a minute. So 4 minus the sine of pi over, 4 sine of pi over 2. Sine of pi over 2 is solid uno. And so 4 times 1 is 4. 4 minus 4 is a big old goose egg. So 0 comma pi over 2. Four minus 4 times the sine of 5 pi over 6. All right. Sine of 5 pi over 6 is what? A half again, yeah. ASTC, top half of the unit circle, sine functions are positive. All right, so we're talking about essentially the same thing that we got when we evaluated pi over 6. So that's just going to be a solid 2. So 2 comma 5 pi over 6. And then when we plug in the pi, 4 minus 4 times the sine of pi, anything on the x-axis for sine is going to have the same result. So sine of pi and the sine of 0 are going to be the same. So whatever we got for 0, we're going to get for pi again. So in that case, 4. All right, So I'm going to go over to the graph now because so far, based on what I've plotted or what I've calculated, we've calculated, we haven't come up with anything that's going to destroy the natural scale of the graph. All right, so 4 steps in the direction of 0 is my first point. Two steps in the direction of pi over 6. 0 steps in any direction is just going to be at the pole. 2 steps in the direction of 5 pi over 6. I just went a little cross-eyed there. Right, yeah, is where I'm looking. And then 4 steps in the direction of pi. 1, 2, 3, 4. All right, so from what I have here, I have enough to draw part of my graph. All right, so this is looking like, well, it wouldn't be a cardioid because just based on the rules, I'll just show you real quick. I'll go back to that in a sec, but the cardioid requires your coefficients to be identical. So if it were 4 plus 4 sine theta, then it would be a cardioid. So this is a limacon, but it's one of those limacons that seems to just have a dimple, not with the loop-de-loop. All right, so that just tells me that I just need a few more points, and I'll have what I need. All right, so unfortunately, it's not like the last one where after we got to pi, we could rely on symmetry and pretty much come up with the entire graph. And in fact, in retrospect, if I had started off with maybe something like, instead of going from 0 to pi, maybe if I did like negative pi over 2 to pi over 2 on that interval, maybe I would have got something that was reflectable. But you don't know that until you start getting into it. All right. At any point, we could have kicked over to the calculator, but again, I said I wanted to do it by hand, so here we are. All right, so next up on my convenient list would be 7 pi over 6. So only reference angles of 30 degrees. So any radian measure that has a denominator of 6, and also the quadrantals. So 3 pi over 2, 11 pi over 6, and 2 pi. Now, it doesn't happen in this case, but it is possible. You could go through all this stuff, all this work, and come up with still an incomplete graph, in which case you go to the calculator or even pick more points. After we go through these points, we'll have exactly what we need, so it'll be fine. But, you know, sometimes a little perseverance, you know, that's the name of the game. All right. So 4 minus 4 times the sine of 7 pi over 6. All right. Sine of 7 pi over 6 is what? Negative 1/2, right? So we're taking negative 1/2, multiplying it by negative 4, so it's a positive 2. So 4 plus 2 is a positive 6. All right. So 6 comma 7 pi over 6. Now, old expression, if you don't learn from history, you're doomed to repeat it, or something like that. When we evaluated pi over 6, we got our answer of 2 comma pi over 6. We did the work to get it, and then we realized 5 pi over 6 is going to give us the same answer. So everything on the top of the unit circle for those reference angles of pi over 6, they were just going to give us the same result. So bottom of the unit circle, we can expect the same thing. All right. So without doing the work, I know that 11 pi over 6 is going to give me a 6 comma 11 pi over 6. And that's because the sine of 11 pi over 6 is also negative 1/2. So it would give you the same exact calculations. We also learned that 0 and pi, since they're on the x-axis, they gave us the same result. Well, 2 pi is also on the x-axis, so it'll give us the same result too. So 4 comma 2 pi. Now, that one's a little extraneous because the reality is 4 steps in the direction of 2 pi is exactly the same thing as 4 steps in the direction of 0. So we're not going to get a unique point anyway, right? But it's one less calculation to worry about regardless. All right, the only one that we have to compute, and it's not a crazy computation, is this one. So 4 minus 4 times the sine of 3 pi over 2. That's going to give us an 8.
Yeah.
So 8 steps in the direction of 3 pi over 2. All right. So normally I'd say, whoa, 8, we'd have to scale that. But first off, we already started plotting points. Secondly, I think we could ballpark where 8 is. So 1, 2, 3, 4, 5, 6, 7, somewhere down here. You know, just ballpark it. All right, as long as you have the spacing down, you're going to be in good shape. All right. So 6 steps in the direction of 7 pi over 6. That's going to put you about right here. 6 steps in the direction, 1, 2, 3, 4, 5, 6 steps in the direction of 11 pi over 6. Again, we're going to ignore the 2 pi one because that's the same as 0. And then 8 steps in the direction of 3 pi over 2. So 1, 2, 3, 4, 5, 6, 7. It's about right, yeah. And that would be your Loomis sum. All right, so we pretty much got everything we need from it, or needed from it. But a lot of computations here. The other approach, the one that we talked about last class, was put your equation in your calculator, set your table step, your change in table in your table settings menu to pi over 12, so that every step downward in your table corresponds to a ray along your polar graph, and then just look for the clean ones and plot, right? So, or relatively clean ones. You know, if you got like a 3.7 as an R value, that's clean enough. You know, something that you could actually plot. It's when it's crazy, you know, you got something that's like 0.12897. It's like, where am I going to plot that? Ignore that one, you know. So something that's plottable is really what we're talking about. This one, and then this whole page. All right, so cosine of 3 theta. So this is a little bit of a different story because you might you might think of values for theta that are convenient for cosine. Going around the unit circle, that would be your 60-degree reference angles. But the problem is, does that mean that it's going to be convenient for cosine of 3 theta? So not necessarily. So this is a definite calculator situation, all right? So let me bring my calculator in. Let me, gotta bring it right in there. And so in polar mode, let me just make sure I'm in the right mode. Let me also check. Generally radian, but it's up to you. If you're not mixing it with other types of functions, it doesn't matter. All right, so clear this one. -7 cosine of 3 times theta. I'm going to change my table settings. I want it to go by pi over 12. All right, I think that's what I had in there anyway, but just to reinforce how to actually do this, again, you're going to go second window on your calculator, leave your table start at 0, and make your change in table pi over 12. Honestly, I don't know if yeah, I did hit it. Okay, so pi over 12. All right, it'll convert it to decimal form, and that's fine.
Is there any way to change the format of the table, like on the left side, to make it into radians?
Like symbolically?
Yeah.
Unfortunately, no, because it doesn't understand irrational numbers like that. It only understands things that are a fraction form. Like if it could be converted to a fraction, it'll do it, but these can't be. So, unfortunately, you get this ugliness. But there's some good things in there. There's also some nastiness in there. So we just got to kind of navigate our way through it. All right. So let me do that. Each step down, and that's the thing, you just got to keep track. Sometimes you'll lose count, and then you just scroll back up till you find 0, then start counting again. All right. So what I'm going to do first is grab the clean ones. All right. 0, -7. All right. Remember though, they're giving us theta and then r. So we plot this backwards. -7, 0. If you were to write that down, that would be fine, but you don't need to because if all you're doing is creating the graph. You just have to know that you're taking 7 steps away from 0. All right. So that's what I'm going to do. You could also scroll down and make sure that there's not going to be anything more extreme than 7, because then scaling would be an issue. But in this case, there isn't going to be.
Why did you hit that screen? I thought you hit angle.
Second graph, and it'll bring it into the table. The angle menu is to convert back and forth between polar and. So 7 steps away from 0 is what I'm looking for. So 1, 2, 3, 4, 5, 6, 7. That's about 7 right there. So in case you haven't picked up on my little convention here, I count the radians as basically covering up the next ring, and the degrees would be the ring after that. So I have 1, 2, 3, 4, 5. This would be my 6th ring, and this would be my 7th ring. After that, you got to eyeball it, but I just plot it right over the angle, and I'm pretty confident that I'm not screwing up any kind of scaling. All right. The next one, I guess I got to stand up a little bit for this. The next one would be 1, 2, 3, 4 steps. The next clean one, 4 steps away from 0. So 1, 2, 3, 4 steps. That's just so you don't have to actually have a scientific calculator on the side to figure out, all right, what value of pi is that equivalent to? Now, one thing I will tell you, because you're working with exclusively trigonometric-based functions here, you could convert this over into degree mode and have nice degree-related angles here. The problem is, if I even mix in one case where there's another type of function in there, it's all over. Right, so you kind of want to build the right habits, but you could get away with it in a pinch. All right, so here's our second point: 7 steps in the direction of pi over 3. So then I scroll down 5, 6, 7, 8. All right, that's the 8th step because this was my 4th step away from 0. So 5, 6, 7, 8. So 5, 6, 7, 8. And it's also justified because this number looks like it's double that, and 2 pi over 3 is double pi over 3. So that's a pretty solid move. Now 7 steps away from that one. So we're going to go down here towards 5 pi over 3. Now if I keep scrolling just looking for 7s, the next one would be 3 steps in the direction of pi. I already have that. And I promise you, if I keep scrolling down looking for more and more instances of 7s, all I'm going to do is get these 3 same points over and over again. All right, so I need to embark on a journey into decimal land. So with that in mind, let's try to keep it simple. Let's stay close to 0 and see what's going on here. All right, so 1 step away from 0 is going to involve
a R value of negative 4.9. So if I'm standing at the pole looking at that 0.26, which is pi over 12, this is telling me to take 4.9 steps away from that. 1, 2, 3, 4.9. It's going to be just a smidge shy of this last ring here at 195. .52 is equivalent to pi over 6. We're going to take a little bit more than 2 steps away from that. So a little bit more than 2 steps toward 7 pi over 6.
Just curious, how are you able to convert so quickly from decimals to
Oh, I'm not really converting. All I'm doing is saying that this is my benchmark here. Since I set up my scale in pi over 12s, I know that each step down is beep, 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 beep.
about 5 hours?
Yeah.
So you had to know that before.
Yeah, that's why we changed it in the table setting. So we're changing the table setting to match the graph itself.
I got 0.
0.
For the 0.523.
Indeed.
Yeah, so that's it. That's magnifying
Radian. I'm not seeing anything wrong. Just for giggles. Yeah, okay, so that's not it. No, I didn't think that happened, but I just wanted to do my due diligence. Oh man, I took a walk here. Hold on a second. Oh, let me. Second one, 0. Okay, crap. For 0.52, you say you got 0? Ah, son of a gun heck.
Did you put 3p in?
No. Look at that bad boy right there. Scientific notation. Hidden in plain sight. Yeah, this is my calculator's trying to tell me 0, but it didn't do such a hot job of making it clear and obvious.
And the Calc is giving me 3 points incredible. It's 0, 7, 4.95.
0, 7.
4.95.
But it's giving you something that would round to 0?
Yes.
Then that's fine, because that's what mine was trying to do. I just didn't investigate hard enough.
You get -7.
It's heartbreaking.
That's what's wrong.
Yeah, but you know what? I should have picked up on it. But I wasn't looking hard enough. Because it has ... So I should have known something was iffy about that one. But I just wanted to believe it was correct. Alright. It is what it is. I'll get over it at some point in the next few weeks. So 1, 2, 3 steps away, 1, 2, 3 steps away. All right. So now we're looking at 4.9-ish in the direction of pi over 4. So 4, 2, 3, 4.9, so just a shade short of that point there. All right. Now this is strictly a calculator-based approach. So you might say, bless you. I mean, if you study those classical curves, the chart and everything, and you know the characteristics of it, you may already have everything you need. But if it's not the kind of thing that comes natural to you, then you just keep going. So the next point, the 5 pi over 12, is also going to be a point of 4.9. So we're going to be just shy of the 5th ring on that one also. All right. So at any point, you could kick over to the graph I mean, you typed in the equation anyway, so you can take a look at the picture and see what you're up against. When you do that, I'll just zoom in, you could see that you're looking for something along these lines. All right, so this is, they call it a 3-petaled rose. I mean, you look at it, it doesn't scream rose when you look at it, but you know, you just assume that there's plenty of instances where they call something in math class the same thing that you call something completely different in real life, and you just go with it. All right, so if that's the case, then I can really start getting into the diagram here fairly easily, because I know that I'm going to have something along these lines. But then if all of these petals are going to be of the same size, now that might be a suspend your disbelief kind of thing, because depending on how you scale it, it may not even look remotely like they're the same size, but they're supposed to be. And so if that's the case, then we can assume that this trio of points would have to occur for each petal. So then we can now assume, without doing any more work, that these points also have to exist. And then we can finish the job. And so there you have your 3-petal rose. All right. Now there are characteristics associated with these graphs that are specifically related to the functions. So the coefficient, if it happens to be odd, dictates the number of petals, the coefficient of theta. The coefficient of the function itself, if it's in the format of a rose, the leading coefficient dictates the radius of the figure. So the length of each petal would have to be in total 7 units away from the origin. All right, so those are some things that you can rely upon, but it's not going to give you these other points here. So you still have to use some kind of technique to come up with those values, and the calculator ends up being a good resource. If the coefficient in front of theta were even, then you would have twice as many petals in your rows. So if this were cosine of 4 theta, you'd have 8 petals. All right, so it just works out that way. It's just one of those mathematical oddities, but it's a cool one, but not the kind of thing that you need to spend too much time worrying about. All right, because again, the calculator. You know, like if I would like to say that I was in a class, Calc 3, when I took it, that we weren't allowed to use calculators. We might as well not have been allowed to use calculators. We were allowed, just nobody knew how to use it the right way. So it's basically like not having it at all. Right? So in our instances, we needed to know those characteristics because nobody knew how to create the graph on the calculator. So it wasn't going to happen any other way. Right? But here, you know how to do it. You know how to go into polar and parametric mode, and then later on sequential mode when we get there. So all these things are resources that you have available to you, so definitely make use of them. All right. So, that being said, we're going to kick on over to page 13 and calculusify this. Areas and arc length in a polar plane. So finding an area in a circular region is not difficult if it's a uniform circular region. So if you're dealing with like a circle, pi r squared, no problem whatsoever. A fraction of a circle, pi r squared over something, divided by, you know, if it's a quarter of a circle, divided by 4, 12th of a circle divided by 12. But what if it's not quite a circle? You have part of it that's a little circular, but it's not I would not, under any circumstances, call this a circle. I mean, you could probably, if you grab the compass and a ruler, you could probably ballpark a circle that you could use to estimate this, maybe figure out the angle, and then come up with a reasonable estimate of what you think the area is. But it's not going to be very precise, right? Now, if instead of doing that, you took, and I'll zoom in significantly here, extreme close up. Whoa. Oh, hold on, my pen's not working. Let's say I took I'll just leave it on pen. Just this piece. I'll grab the part that actually looks fairly circular. This piece here. And then actually fit a circle to that. All right. Let's see if it works. I always run into the fill problem. All right, undo, undo. False start. On the offense. Again. I didn't change the fill, so why would I expect anything different? Can I do it after the fact? Probably not. Yeah, it's not, I wouldn't call it. Ooh, hold on. I think I got it. Hold on.
Squares, that's like super.
This
There you go.
Oh, it's magic. I think I just moved the entire page to fit my circle, but I'm not even gonna argue that. All right. So you can start thinking about things like this, where you say, all right, well, I got this border here. Maybe I could find the area of this circle, and then maybe I could find, if I take another piece of it over here, maybe I could find a different circle, and then just try to piece all that together after the fact. Maybe do something like this. This would be like a really big one. That's an oval. I'm gonna have to bring it out a little bit to make it work, I think. It's gonna be an oval again. Yep. There we go. It's a circle. I just learned something. If I draw a circle, it'll autocorrect to a circle. But if I don't, it's not gonna. All right, that little, oh, okay, hold on. I gotta move this down the line. All right, this should be like, yeah. That should be it, right? Just hit that bad boy?
Yeah, it's one of those squares. Try the one on top.
Oh, I see what you're saying. Alright, well, you get the idea. So none of that's going to work. Because what's going to happen is, and you just take my word for it, because obviously this is a long way from where it used to be. I used to try to hand draw all that. It's not a nightmare. What's going to end up happening, and you can kind of see from my little false start on my diagram, is that the circles that I draw, the big one to account for this part would overlap the circle that I created to account for this part, and I'd end up having to subtract and add little pieces in here and there, maybe use an area of a triangle formula to get some other parts. It's a mess. All right, so maybe doable with geometry, but not in a reasonable way. The better way to handle it, I still have to actually try to draw a diagram, so here we go. This one is just a line though.
what if I take a little tiny sliver? And you know, in calculus, little tiny slivers are kind of the name of the game, right? You've been working with little tiny slivers ever since the beginning of Calc 1, right? So this little tiny sliver here represents the sector area of some circle centered at 0, 0. All right. So that little tiny sliver represents some sector area. A sector area of some circle centered at 0, 0. I could fill it in. I'm not even going to bother trying to use the fill tool. It's not going to work, at least not for me. All right, now, hit or miss as to whether or not you remember that from pre-calc. So I'm going to elaborate over on the side here. Sector area. It's a slice of pizza. It's a technical definition. I'm going to draw a circle. That is not an angle. I'm going to live with that one. This is the sector area. So it really is a slice of pizza. All right. Now, if you want the area of that little sector, you'd use the formula. Area is equal to 1/2 r squared times theta. All right. So you have some given angle theta, central angle, that corresponds with that slice of pizza. You have a radius that corresponds, so I'll just jot that in there. Radius that corresponds with the circle itself. By finding 1/2 r squared d theta, I'm getting ahead of myself, 1/2 r squared theta, you're able to find the area of just a single circular sector. All right, I'll give you a quick example. Let's say you wanted to find the area of a circle, just a whole circle. That's the same as a sector with theta equal to 2 pi. That's the case of you have an entire pizza pie. You ask somebody if they want a slice of pizza, and what they do is they grab a slice, and then they're like, you know what? Hold on a sec. Put that on their hand. Then they grab another one, put it on top of that, and then another one, and then another one. Before you know it, they have 8 slices in their hand. They took the whole pie. All right? That's what's happening here. So they're taking the entire pie. That's what's going on in this problem. So 1/2 r squared theta, 1/2 r squared 2 pi. Simplify it, pi r squared. That's the area of all of the sectors that make up one entire circle. All right, which is the formula that you know and love, area of a circle. All right, so this is a little mini proof of the area of a circle formula. So it's not anything earth-shattering, but it kind of gears us into the, sets us up in going in the right direction. And it also allows for you to believe that what we're about to do is a valid technique because we've just seen it demonstrated with something that we're very familiar with. All right. So
this little sector is part of some ginormous circle that we're not going to illustrate just because I'm not physically capable of doing it. Maybe you can. Now, if I were to go out even further, I would have another little sector. I can get another one going here. Put it right next to it. Now, I like to think of it as a circular instead of sector, a circular sliver, but I don't want to introduce too many terms to confuse people. All right, I can't even move it, so I'm not even going to bother. I'm just going to leave it there, and just, even though it doesn't look perfect, I'm just going to establish that. All right, so it's still pinned at the origin, but we have another circular sector, but just a smidge more, all right? And then we could build outward across this entire field based off of that distance. Or, I'm sorry, based off of that technique, all right? So I can go here, here. I'm gonna have to clean this up a little bit in a minute, but, and so on. I'm just trying not to look at the origin, because everything's fine if I don't look at the origin. That one's terrible, so that's gotta go. I would say that if I put even the slightest amount of effort into trying to make the tracer line a little bit better, then my diagrams wouldn't be so bad, but I'm not. So here we are. Look at that one. Oh. Oofa. All right. So I'm gonna hide the evidence. Problem solved. All right. So all of those little sectors, they amount to their own. They have their own circles, and each one of them have these like infinitesimal little areas. And if I were to add them all up, I would have the area of this entire sector. All right. So very theoretical stuff, but it's worth the time to investigate because we can actually get into the derivation of the formula, which comes right below, but I'll just do it off on the side. I could say area of an infinitesimal sector. Infinitesimal is a big word with lots of letters, so we're going to say a tiny sector. All right. So 1/2 r squared. Now, the theta movement, all right, that's the little issue that we're running into here. The r value is always going to be the r value. It's related to the function, all right? Now, this is a variable r value. So this could be r in terms of theta. So that's another challenge that we'll have to deal with. But the thetas, and I'll show that here just with little arrows. They're teensy tiny movements in theta. When you have a teensy tiny movement in x, we called it dx. A teensy tiny movement in theta was known as, will be known as d theta. So tiny movement in theta we call that d theta. All right. So we're not talking about that area of tiny sector being 1/2 r squared, some large angle. We're talking about it being 1/2 r squared, some teensy tiny angular movement. So d theta. All right. Now, we learned when we were talking about arc length for the parametrics that if we collect all of those teensy tiny little pieces of the puzzle and put it all together, we're integrating them together to give one total. All right. So I have an interval that's starting at alpha. That's not an alpha. I'm like, I can't stop myself. Hold on. Because I'm doing it backwards. That's why I'm like, why am I trying? I'm continuously trying to make a script L, and I can't even stop myself. So alpha and beta. Beta's easier. All right, but most people go A and B. But when you're dealing with angular movements, we try to go alpha and beta wherever possible. It's up to you if you want to do that. I'll let you off the hook if you don't, only because you saw like 4 attempts for me to make a reasonable looking alpha, and I screwed it up 3 out of the 4 times. All right, so.
Why didn't you just have the letter A and B?
Well, the A and B are usually reserved for rectangular bounds.
Yeah.
And so the angular bounds, we usually use alpha and beta. For now, you could go A and B, it's okay. But later on in the course, when we get to spherical coordinates, we're going to have to use alpha and beta anyway.
This is A and B in the back. Not on the graph, but in the formulas. What I was saying here.
Typo.
I call it. I'm calling it in.
Yeah, call it in. Yeah, those should be alphas and betas. I got bit by the copy-paste monster. Over the years, I've gotten really good at answering the question that wasn't asked on. But I thought you were talking about the rationale for why we're using it. You want to just type on. Okay, so 1/2 r squared d theta. All right. So this ends up being the total of all tiny sector areas. All right, so if I take all those tiny sector areas and add them together, I would get this. Right? Integration allows us to do that in one shot. Area between polar graphs, I don't think that needs a derivation. I'll just talk about it very briefly. What that's telling you to do is find a 1/2 r squared d theta for the outermost outermost polar graph, and subtract from it a 1/2 r squared d theta from the for the innermost polar graph, right? And that's basically the idea associated with area between 2 curves. You find the one that contains more area, the one that contains less area, find those 2 areas, subtract the 2. That's what's happening here. It's just it's all put together in one concise formula. But conceptually, it's really just find the area bounded by the 2 functions separately and subtract the results, but over the same interval. So that's the tricky part. Then you have the arc length of a polar graph. I already hit you with an arc length derivation. We do that for parametrics. This derivation isn't such a far cry from what we've already done. So it would be like beating a dead horse. Although that's an archaic term and it's pretty terrible, so I'm not going to say that anymore. But also it should be alpha and beta here as well. Actually, all 3 of these should be alpha and beta. But I'm not going to bother with the derivation on that one because it's not going to advance the plot. All right. So I was thinking of should I derive the formula for you, or you know what? I'll do it next time. Star on it. Not a star. Let me just highlight it to remind myself, because I'm thinking about it and it's probably worth
even though it is similar to the other one, it's probably worth spending the time to look at it. I just don't think. So, let's tackle a problem or something. Sketch the figures and find the arc length and the area of each of the following. All right, so the sketches are variable. It depends on the nature of the file, but you don't need me to tell you that. So I don't even have to be talking about polar graphs to think like that, you know? Like if it's an easy equation, it's gonna be an easy graph. If it's not an easy equation, it's gonna be a rough graph. All right, so that's the same idea here. All right, but r equals 3, we learned 2 classes ago, maybe 3, that this is the equation of a circle with center at 0, 0, and radius equal to 3. All right, which is good news and bad news. It's good news because that means that you know that you could find the answer without calculus. It's bad news because we have to find the answer with calculus. All right, so it sucks. It's like I already know the answer, but actually no, I'm overselling that. It's a good problem to start with because when when you have a problem like this and you already know what the answer is going to be, I mean I can throw this one on the test too. You know what the answer is supposed to be. Once you get that answer, you're pretty confident and you can move on to the next one with not a care in the world. All right, so we're gonna start with the well. It said, oh, you know what? That's a legacy typo. That typo's been there for like a solid decade. It's not a significant one. It's just one that bothers me. Find the arc length and area. Switcherooski. Because I introduced area first and then arc length on the previous page. So for consistency, even though it says find them both, I gotta do them both. I want the directions to lead the reader to think area first, then arc length. All right, so that's a typo for somebody if you want to claim it. I'm pretty sure I pointed that one out before. It's just nobody's ever claimed it. They're probably thinking somebody else is going to get it. All right. So, well, we could do the diagram pretty easily. You don't need a calculator for that. I'm going to pretend that's a circle. Its radius is equal to 3. All right. Using a step of 0.01. All right. When you're sketching a figure and I give you a theta step, and that theta step is really small, all I'm telling you is that it should be a smooth curve. All right. So smooth curve. All right, if the theta step were large, then you'd be looking for something more angular. All right, so we got that part. Now, what we're gonna do is apply our rule. All right, we know a circle, like any circle, is gonna go around 360 degrees or 2 pi radians. So it's gonna start at 0, it's gonna end at 2 pi. So my domain is consistent in that it represents the beginning and the end of the graph. I don't have to worry about this being one of those kind of graphs that's going to wrap around itself a couple of times based on the domain. Now, if this said r equals 3 on 0 to 4 pi, I would be concerned because I'd be like, wait a minute, a circle begins and ends in 2 pi radians. So if it's 4 pi, it may go around a couple of times. For area, that it wouldn't matter. You know, like it's one of those things where once you figure out where the circle begins and ends, that is the area that will be captured. You can go around it 20 times, it's still going to be the same area. But for arc length, it does matter because I'll tell you right now, if I'm running around a track
and you tell me I got to run around it 30 times, I don't care how much area is contained within the track, I got to run around the edge of that thing 30 times, that's going to be a problem. All right, so arc length, it matters in terms of the length. So in that regard, you just go with it as is. The area, you have to be very careful about where the graph begins and where it ends. All right, so this one's a simple case. In other cases, I'll walk you through it. You would need to either use the calculator to support or solve for where the graph hits the polar axis. Right, and I'll show you how to handle that also. All right, so bottom line is I could jump right into the 1/2 r squared d theta. So area is equal to 1/2 on the interval. All right, we're starting at 0, going to 2 pi. 1/2. I'm going to write it in general terms first. R squared d theta. Now you could integrate this as is. As it turns out, that theta is the integration variable, which means that r could be treated as constant, which is actually the foundation of multiple integration. But that's a different story for a different day. What we're going to do is, since we know that r is a constant, r is 3, and it's always 3 in this world, I could just chuck that right in. And we'll be looking at the antiderivative over the interval of 0 to 2 pi. This is going to be 9/2 d theta. All right. Integrate, we're looking at 9/2 theta over 0 to 2 pi. Plugging in the 2 pi gives you a 9 pi. Plugging in the 0 zaps away, so we're looking at 9. Why is this glitching on me? Come on, write something, for crying out loud. Now it's writing stuff that I don't want it to write. So it's going to be 9 pi. All right. This is one of those cases where, yeah, you can put it in the calculator, but, I mean, it's a constant that you're integrating. You just slap the variable on it and call it a day. You know, so this is not something that you should shy away from doing by hand. Right? So that's the area, 9 pi. Well, area is pi r squared, right? Radius is 3. Pi times 3 squared would be 9 pi, so we're comfortable with this as a final answer. All right. So then what we need is the arc length. So we know that the circumference is something that we could figure out pretty easily also. All right. So going into the problem, we know what we're up against. So arc length, S for some reason, over the interval of 0 to 2 pi still, the square root just debating. But you know what, let me is that time. All right, that I've come to a decision. All right, so anyway, r squared, so 3 squared. And then it's the sum of the squares, so plus, I need dr d theta squared. Well, r is equal to 0, r is equal to 3, stole my own thunder. Yeah, so r is equal to 3, so if I want dr d theta, derivative of a constant is equal to 0, so 0 squared.
because it's really the sum of the square part of it that I want to get across, the Pythagorean relationship. It's actually pretty cool, so it's worth looking into. But I think we'll do that. We'll do that beginning of next class. Okay, so 0 to 2 pi, looking at 3 d theta, integrate, looking at 3 theta over the interval of 0 to 2 pi. And then when you plug and chug away, you get 6 pi minus 0, so 6 pi is it. Oh, my pen turned off. That's why. It's not glitching, it's just off. A little bit. Yeah, I'll actually charge it today. So
Are those charge like really fast, like a minute, like full battery, or something like that?
yeah, it goes pretty quickly, but I think I'm also like I struggle because I'm a little colorblind. I know when this starts turning purple, that's when it goes purple then red.
We've got it blue right now.
It's solid blue, right?
Yeah, it's solid blue.
Is there a hint of purple in there?
Maybe.
Not that, okay, so. Yeah, that's the whole issue. And also, there's the other thing.
Why do you have to turn it off?
Oh, because it's, what is it, they call it an adaptive pen? So, this interface won't work unless it's powered. This one will. So this is just a regular stylus, this part of it. But this part is like, it's not an Apple Pencil, it's not Bluetooth, but it's, yeah. So it'll actually, you know, the weight of the writing will vary depending on the pressure put on it, but only if it has the power behind it. Oh wow, the Mets won. They pulled it out in the ninth. Look at that. I mean, the season's over, so it doesn't matter. But like, that was nice. Because before class started, I took a look and it wasn't looking good. Oh, Alonso, 49th homer, rookie of the year. It's just another instance where a Met's gonna have an individual accolade for the team stuff. Yeah, so circumference of a circle is 2 pi r. Double the radius, you get 6. Multiply by pi, you get 6 pi. So we're in pretty good shape there. So we're verifying really that this is not the demonstration of intense Calc 3 knowledge and polar coordinate stuff. However, I think you'd like it to be, because if I put many problems like this one on the test, you'd be thrilled. Because there isn't really much to do, right? And even the integral part of it isn't that bad. The one thing that, one of many times I'll say this, that you need to be mindful of this, is that the integration stuff is not the thing that should be intimidating you in this course, all right? You've already been assessed on that. I'm not looking to assess you on that again. So anytime we come across an integral, if it's a definite integral, pop it in the calculator and move on. All right, it's different in other people's classes. I don't care about other people's classes. This is my class. In my class, you're allowed to use a calculator to get the solution to definite integrals. There will be plenty of instances where you have to do indefinite integrals by hand. You'll earn your keep on that. So when you see a definite integral, so you're given bounds, chuck it right in the calculator and don't even give it a second thought. Because if you spend time trying to do that kind of thing out by hand, it's time that is not well spent, all right? You're gonna run out of time for something that does require you to work it out by hand. All of that is me gearing us up for number 2, because this is not a circle equation, it's a limacon, all right? And in that limacon, we got our work cut out for us, all right? We have to create the sketch of the graph first. All right, so as easy as number 1 is, that's how difficult number 2 is in comparison. All right, so just kind of getting you oriented. All right, so first thing we want is a sketch, and the reality is you want the sketch.
You do not want to shy away from the sketch. You don't need to do it by hand though, all right? A sketch is a sketch. The only time that you need to actually have it by points is when I say create the graph, and you know, I'll say things like be sure to include the scale and label this, that, the other thing. But if I say create a sketch, a rough sketch is fine, but it still has to be there. All right, so let me get the calculator out. So we're looking at clear 2 plus 4 times the cosine of theta. I'm just going to graph it. This is our Lima sum. Structure is all we care about. I want an idea what this thing looks like. All right, so, and again, sketch. Yeah, I'll give you your sketch right here. I'll show you your sketch right here. Look at that. Perfect sketch. Full credit. All right. The characteristics are what's important. I'm done with this. We're gonna do everything else. At least until we get to the part where we have to integrate stuff, we're gonna do everything else by hand. All right. So I need to know where this graph begins and where it ends. Sometimes watching the graph actually be generated on your calculator, sometimes that gives you a sense in and of itself. But we could also solve for it. We know this graph is going to go through the pole. All right. So if you actually watch it get graphed, you'll see it'll start here, it'll go through the pole, it'll wrap around, and then it'll finish up here. All right. So what I'm going to do is a couple of things. I'm going to find where this equation is equal to 0. So, and that's a classic calculus technique. Honestly, if you think back to Calc 1, Calc 2, if you were ever in doubt, I have no idea what to do with this problem, take an equation, set it equal to 0. It's probably the right thing to do at some point, right? So that's what we're doing here. All right, so 0 equals 2 plus 4 cosine theta. I'm going to subtract the 2. So negative 2 equals 4 cosine theta, which means cosine of theta, if I divide the 4, it's going to be equal to negative 1/2. A unit circle thing, it's just there all the time. It's crazy. It's like I wasn't lying before when I said the unit circle is important. All right, so going around your unit circle, now we're forced into the world of radians here. In some cases you have a choice, in this case you don't, because the domain given to us is in radian form, so we're stuck with that. All right, so going around the circle, we know that in the second quadrant and in the third quadrant, cosine is negative. That happens at 2 pi over 3 and 4 pi over 3. All right. So that tells me the angular measures for which the graph, and I'll highlight it here. I'll just do a little, oh, no, that's not what I wanted to do. Scroll up a little bit. Undo. Scroll up a little bit. I'll underline this, and then I'll highlight the point on the graph. That tells me where it's going to cross the pole. All right. I would also need to know where it's going to cross that polar axis. All right, so you could start thinking in terms of that, but I think that's pretty straightforward, because if you're just looking at the picture, well, if it's on the polar axis, in terms of theta, that's going to happen at 0 radians. All right, because it starts at 0 and ends at 2 pi. All right, so here's my 0 radians. 0 radians, not ORAD. But then it works its way around in this direction, then this way, and this way, and then finally this way. So then it finishes up at 2 pi. Alright, so you're getting a sense of the characteristics of the graph. But like I said, sometimes just looking at the picture gets the job done too on the calculator. So let me bring that back up and show you how you could kind of wiggle your way through that information without going too crazy with the algebra and the trim. So in your window, the first thing that I would recommend is verify that you're only going to get one complete loop in the given domain. All right. So it might be weird to think like how can I verify that? Well, the default is 0 to 2 pi. I can clear this out and type in 2 pi and be really sure that that's the case. Yeah. Okay. There's the whole graph. Now, instead of 2 pi, what I'll do, so I'll hit enter, it converts it to decimal. I'll just dial it back a smidge. All right, instead of 6.28318 blah blah blah, I'm gonna put in 6.2. All right, because if I dial back my theta max a smidge, just short of the full domain, then I should have just short of a full graph. So hit graph, I have just short of a full graph. All right, so it looks like I'm not at the point where I would be worried about overshooting it. But let's say, for example, and I'll show you where this really becomes an issue. The problem says 0 to 3 pi in the domain that's given. It's the same graph as 0 to 2 pi, right? I will have overshot the endpoint by a lot. All right, so it would have started here, it would have went around, it would have completed the loop, and then it would have started the loop again. All right, but it's overwriting the graph that's already there. So then I would say, okay, well, is that too far? So let me try 2.5 pi. It's still too far. All right, so then I'll try 2 pi. Is it too far or is it just right? I don't know. So I'll try something a little bit less than 2 pi. And that's where I settle in on, clear 6.2. 6.2 is just a smidge less. So a smidge less than the full domain should give you a smidge less than the full graph. All right, so that's a way of verifying that what you're dealing with is the entire graph over the given domain. And you can do the same thing with the circle. You know, if you had r equals 3, you plug that in. Instead of having it go from 0 to 2 pi, have it go from 0 to just a smidge less than 2 pi. What's that?
I don't think it's up in the middle. I think it's 10.
Doesn't? They screw it up?
Or 1.
The plug-in is 0. Oh, it should be 6. Yeah, sorry. I identified the wrong spot. Yeah.
I just put a 1 there, just like where it started.
Yeah. So that's the other thing. Okay, so let me just fix that. Which is weird because I had it labeled correctly initially, and then I just deviated from that for some reason.
That can be right.
Yeah.
Yeah, that's the beginning. And then everything else I think is, let me get rid of the 2 pi. Now you could actually watch a graph on your calculator, so that's kind of a nice thing. It's actually a pretty significant flaw in the programming of the calculator, but it's a flaw that you could benefit from, so it's good. But for me, it just appears, right? So if I want to get a sense of how this graph looks, I could just start working my way around. 0, instead of going from 0 to 2 pi, I can go from 0 to like 1, like you said, graph. That gives me a little bit of it. Then maybe 2. Then maybe 3. Or I'll just go right to pi at that point. That gets you halfway there. And then continue on the journey and you'll see where you're at. All right, so now we have a sense of the nature of this. Now, what we figured out earlier was
Where the graph would hit the pole. That's going to happen on the 2 pi over 3 to 4 pi over 3 interval.
all right. So let's actually take a look at that. Two pi over 3 to 4 pi over 3. You'll see that that gives you just the inner loop, because that's where the inner loop begins and where it ends. All right. So we're starting at 0. We first hit the inner loop. I can make a note of that. We first hit the inner loop when theta is equal to 2 pi over 3. Then we work our way through the loop, and then we come out of the loop when theta is equal to 4 pi over 3. And then we continue our way on to 2 pi. All right. So now that we have a good sense, or at least hopefully anyway, that's the plan,
By exploring on the calculator a good sense of the nature of the graph, now we can dive into the area and the arc length. So let's focus on, again, the area first. 1/2 r squared d theta. Well, we have an r. That's great. We have an interval, kind of, sort of. But then that's really it. All right?
so the one thing you do not want to do so this is a big no-no. I'll write out the incorrect integral, and I'll tell you why it's incorrect. So from 0 to 2 pi, let me actually use legible penmanship. One half the r squared d theta. All right, with the r being 2 plus 4 cosine theta. All right, that's a mechanical approach. You didn't think at all, and in doing so, you came up with something that will be utter and complete nonsense. All right. And honestly,
You'll get what you deserve because you didn't study. That's why that happens. All right, it's kind of like volumes of revolution. I remember that from Calc 2. The disk method and the washer method and all that stuff. It's like, all right, I got a formula. I know I got to put the function in here somewhere. I'm just going to dump it in and hope I get some kind of partial credit. So you got some partial credit, but you didn't get full credit. Why? Because you didn't really know why it worked the way it did. All right? Let's see if we can figure out why it works the way it does. If I go from 0 to 2 pi, remember, we're talking about infinitely many of those little circular sectors, all added up. If I go from 0 to 2 pi, I'm going to grab the circular sector going the full length all the way around. I'm going to keep going. And then I'm eventually going to get to theta equals 2 pi over 3. All right? Then I'm going to double count that inner loop. All that area in there is going to get recomputed because the next part of the process is going to have that integration formula is not going to stop. This is still part of R. It's going to account for all possible areas between the pole and the curve. So it's going to figure out the area of all of this in this inner loop and add that on it also. And then it's going to keep going back around 4 pi over 3, continuing on all the way up to 2 pi. So what it's going to do is it's going to do a complete double count of that inner loop. All right, and that's going to be a problem because we're going to get an area that's way too much. All right, so in terms of area, I don't want that inner loop to be double counted. Whereas for arc length, I want that length to be accounted for because if I got to run around this track, I'm not a big runner, as you probably imagine. So I want every step accounted for. So if somebody's like, yeah, so you ran 5 miles. I'm like, no, I ran 5 miles and 37 feet. You're gonna give me every freaking foot that I ran because it was torture for me. Like if we can go to the nearest like 1/4 inch, we would do that too. Like you're gonna give me everything. We're gonna know how much I ran, all right? For area, it doesn't matter. We just want the inner region. So we don't want to double count that. So what we're going to do
is find the area going from 0 to 2 pi over 3 of 1/2 r squared d theta and then we're going to add to that the area going from, I'm going to just, it's not working as well as I want, going from 2 pi over 3 to 2 pi, 4 pi over 3 to 2 pi. Of 1/2 times 2 plus 4 cosine theta squared d theta. And we're going to get the sum of that. And we're going to ignore the inner loop.
we're going to pretend it's not even there. Because all we would end up doing if we found the area from 2 pi to 4 pi, 2 pi over 3 to 4 pi over 3, is we would be double counting it anyway.
Did you know what those numbers something
Which one's the 2 pi over 3 and 4 pi over 3?
Yeah.
Oh, so this is all unit circle related. So once we got cosine of theta equals -1/2,
Yeah.
on the unit circle, you're just looking for x values. As the coordinates, the x values are -1/2. The angles that go along with those.
Oh, okay.
So it's all unit circle.
At this point, we still don't know. We are just assuming it's 2 pi over 3. Or is it, do we know definitely it's...
We know definitely it's 2 pi over 3 because that brings us to the pole. Okay, because when we start here, we hit the pole at 2 pi over 3, that's the beginning of the inner loop. And then we hit the pole again at 4 pi over 3, that's when we're coming out of the inner
Because
loop.
we plugged it into the calculator?
Because we did this work here.
What kind of supply link for math model? I don't know, it's different.
What's that?
Or those graph plugins, the one that
Limason?
Limason. So this only applies to Limasons, like you don't have to worry about.
You don't have to worry about an inner loop for anything else.
Just Limasons?
Just the Limasons, yeah.
Okay.
Could you alternatively do the whole formula and then subtract out the other one?
Absolutely. Yeah, so if you did 0 to 2 pi, got of the same function, and then subtracted off of that 2 pi over 3 to 4 pi over 3, same thing. One way or the other, you got 2 computations ahead of you. All right? But the good news is, again, you're looking at 2 pretty hairy integrals here, right? Like if you had to do this by hand, you'd have to actually use a double angle identity for cosine in order to simplify it, because cosine squared is not easily integrated. When you distribute that out, I promise you, it's a mess. All right? You believe me, and we move on. So we type this into our calculators, and we just
we're just thankful. Let me just get out of here because now I'm just like stumbling around. All right, so math 9. Zero. And I'm going to put the 0.5 open paren 2 plus 4 cosine theta.
How'd you get that 0.5?
Oh, the formula is 1/2 r squared d theta.
Right, but how'd you get that then? Like, how'd you in the calculator?
Oh, I just typed 0.5, like the decimal point. Now, how did I get the function itself?
No, like,
Let me see, because oh, just do it in. You'll have to use double parentheses. Yeah.
oh,
Alternatively, put the 0.5 before you bring the integral function up because it's coefficient. So d theta. Gotta get my upper bound in here of 2 pi over 3. Now, normally I would say, let's just do it all in one shot, but I don't want to type all this stuff again. So what I'm going to do is I'm going to hit enter, get that number, and then I'm going to hit second enter, or you can hit the up arrow on these calculators, but second enter works just fine too. Change this to the bounds that you want. This one should be 2 pi. And this one should be 4 pi over 3. So I have this computation, and then I'm just going to add to it the previous answer. All right, just so I don't have to worry about retyping that hairy decimal. So second negative symbol. All right, so that's in lieu of actually storing it in as a dummy variable. At least not tonight. So 1/2 r squared d theta. Looks like my structure is correct. My bounds look good. 0 to 2 pi over 3 for the first one. It gave me a 17 and change. The second one, 4 pi over 3 to 2 pi. I'm taking that and adding it to the previous answer, second negative symbol. I'm going to hit enter, and I'm going to get that number, 35 and change. You might take a look and see if it's some multiple of pi, just to see if there's a way of writing it as a clean answer. Otherwise, just put the rounded answer down. So I'm going to divide it by pi. It doesn't look very clean. I'll try math fracking it. No, it's not going to be clean. So 35.525 is what we're settling in on, approximately. And I hit enter again for some reason, I don't know why. All right, so try it on yours, because again, this one I'm still just getting used to. It's entirely possible I have something terrible.
let's see.
35-ish? 35.525, something like that.
Yeah, that's good.
Because I'm worried that I messed up, so.
I tried that.
All I want you to do is
So I brought this here.
6.7.65.
I feel like I'm missing a coefficient now that I'm looking at yours. $7.511. feels right. The reason I'm pausing is because my number feels absurd. So
7.5.
Not the same.
I just took and then I got the same answer.
You have the same answer. Yeah, that actually would make sense if they were the same answer. Huh. I mean, I guess I'm kind of rooting for my answer.
I think you actually have to see this.
Well, if this were a circle, it would have a radius of around
Oh,
6.
I think the square is supposed to be on the inside of that obviously. On the bottom one. Or both. I think it's squaring all the entire.
I did the subtraction and I got the same thing. You got 35 points something.
You got the same
Yeah.
thing as me? Okay, so I think it might be alright. Now I'm wondering about you.
You're supposed to just do both of them and add them together.
Yeah,
I got 13.79.
you got 13.79 ish. Damn it.
if it were a circle with a radius of 3, yeah, because diameter is 6 roughly, radius of 3 pi, yeah, 35 just seems so large.
I think you're right. That's what I got. 35.5.
35 foot batteries.
Yeah, that's exactly what I got. I just forgot to square it last time.
Yeah, I'm not seeing anything wrong. Yeah, this looks right. How do you scroll? Oh, hit enter.
Oh.
And then you can scroll over. Oh, okay. You only have cosine squared. You want the whole shebang squared. 2 plus cosine. You gotta close it up for cosine, close it up for the function, then square. So you want your power of 2 to be after that.
Because for whatever reason, cosine theta close parentheses squared on your calculator is just the cosine being squared.
Oh.
So you actually have, on those calculators, have to have a double parentheses in order to make it look right.
That's what I did. I noticed that.
All right, so we're gonna live with the 35 and change, at least for now, and then if anybody comes up with a
Mistake on that, then it just feels foolish. All right, now the good thing is for the arc length,
you don't have to worry about really anything that we were concerned about for this part of the problem. All right, so that's the great news. All right, so and you'll find that that's the case for a lot of topics where there's a lot of minor details that could throw you for a loop if you're looking at it in one regard, but then it simplifies a great deal if you look at it in a completely different regard.
So it doesn't be completely correct. You don't have to draw any other work.
Correct. Yeah, I don't want to see anybody trying to integrate this by hand, right? Because then I'll have to grade it, and then I'll have to take off points for stuff that I don't value in this course.
That's what I'm talking to.
Yeah, exactly. Now in Calc 2, I'd emphasize it and I'd penalize and all that stuff, but in this class, it's not something that I'm looking for. All right, so for arc length, straight from 0 to 2 pi, the sum of the square values, so r, which is 2 plus 4 cosine theta squared, plus the second part is a little hairier, you need the derivative of r as a quantity squared, d theta.
All right, so I just need, so here's my r right here. I just need the derivative of this. Constant goes to 0. What's the derivative of 4 cosine theta?
Give you that. -4 sine, yeah. Now, for this one, you could do some simplifying before you get hot and heavy into the calculator, but it's not really necessary, it's just up to you. It's just if you do the simplifying, you could find yourself with a beautiful identity that could make what you have to put into the calculator that much easier. So let's go down the rabbit hole a little bit, but if things start getting out of hand, then we know that we have a bailout. The bailout is Math 9 in your calculator, all right? So distributed property on the 2 plus 4 cosine theta is going to be 4 plus 16, because you're going to have the outers and inners, so you got to FOIL it out. So 8 cosine twice, so 16 cosine theta plus 16 cosine squared theta. Then if you square the other part, you're looking at a 16 sine squared theta, so plus 16 sine squared theta. Now this identity we're going to be working with fairly frequently in this course, so it's worth taking the time to reinforce it now. Let me get rid of the calculator for a minute.
All right. We know that cosine squared plus sine squared is equal to 1. This is just a constant multiplier of that.
All right, so what I can do is factor out a 16, and I'll have cosine squared theta plus sine squared theta. So that's what this part is equivalent to. And cosine squared theta plus sine squared theta is equal to 1, so it zaps away. All right. For this particular problem, do you need to do that? Absolutely not. You just take that top red line and just chuck it in your calculator and get an answer and call it a day. But for the sake of future self, it's worth looking into, because down the line, when that technique is necessary, you're going to be thinking, wow, I'm glad I'm used to that by now, right? Because it won't be a thinking part of the process. So the common factor of 16, we yank it out. Cosine squared plus sine squared is equal to 1, so we just cancel it away. So then we have some like terms. The 16 and the 4 can go together to give us a 20. So 20 plus exactamundo. And so at a minimum, we have something much easier that we could type into our calculator. And that's all for this kind of problem. That's all we're looking for. We're not looking for anything more elaborate than that. We're just looking for something that's nicer to type in. All right. Later on, we'll be looking for even more, but for now, not the objective. So, Math 9 on the interval of 0 to 2 pi. Let me just chuck in the 2 pi. Square root of 20 plus 16 times the cosine of theta. Close it up. No power. That's something. Call that a win. So you'd have double parentheses all over the place if you had that first expression that you typed in. All right, so here's hoping. We're looking at something in the neighborhood of approximately 26.73. All right, not overly concerned with rounding in this course. So however you round, that's fine by me as long as you round it correctly. Because the one conversation I'm hoping to never have again
It's such a weird conversation. You said it didn't matter how we rounded. Why did you take off a point? You're like, well, I took off a point because you rounded to the nearest tenth. You just didn't do it right. Now you can round any way you want. You just got to do it right. All right. So that's the important ingredient. So that, as long as you have that in mind, I think you'll be okay. All right. So answers in exact form, that's a different story, but I wouldn't worry about that too much. All right. You'll be surprised. There'll be some questions on the first unit test where you'll be like, "There's no way this is the right answer. It's hideous. It's the right answer." All right, because you went in decimal form. It's perfectly fine. If you wrote it in terms of pi, it would be much nicer, but it doesn't get you any more credit. All right, so pop a star on number 3, whoever Papa Star is. And that's going to be part of your homework. We'll go over that next class. So that's it for tonight. If you have any questions, stick around. Otherwise, have a wonderful evening, and I'll see you on...
You say you're gonna take out points for decimal positions? Because mine is giving me 1 decimal point less. I'm getting 26.73. Is that okay?
It's giving you 0.7. Oh, you took a staple? Oh.
Yeah,
It's just not big deal.
yeah, it's fine if it's
Okay.
right there, yeah.
It's the only thing we get.
For the first unit.
The first unit.
7.7.
So we just, like,
Yeah, we're going to get more factors. Yeah.